All right, so guys, now we're doing the same thing, except now we're including set theory. Okay. All right, guys, so there's an example on the board. I'm going to give you a few minutes to try to work this one out by yourselves. Do it in the way we did already, and then after that, I'll show you how we include set theory as a part of this. Think of it like winning to 4 or something. What? No. Only because I feel scared for some use the bed if I found the letters of myself. Now I have to go on to today. Yes, I know. Yeah. So yeah, no, stop thinking. Let's go. As the footprint you guys, the surplus must drive. Cheap on the answer. Call not text. Can you see this? Okay, guys, I'm starting now with number 1. How many outfits can you make if you have 9 shirts and 5 pairs of pants? So again, this one is quite straightforward. We can think about it just like with, guys, please. We can think about it the same way we did with the milkshakes example. So I don't know how to draw a shirt, something like, just draw a shirt there. We have 9 of these. Just roughly 1, 2, 3. I'm not going to draw 9. That's going to be too much. It will be 9 of these. And for each shirt you have, yeah, let's do that. For each shirt you have 5. So pants is just 1, 2, ... 5. Right. So if we just count all of these at the bottom, if we list it out, it will give us the number of outputs. Or in other words, if we just want to do this the way we learned, the shortcut method is 5 pants times 9 shirts, which gives us 9, 18, 27, 36, 45, right? 45 options. Okay. That's the way we would have done it. How do we do this using set theory? Let's see, maybe we should do number 2 first, and then we'll do both using set theory. So first, number 1 is done. Number 2, in the way we would have done it, is if you have to pick only a shirt or only a pants, how many options do you have? And that's just like the hot dogs and donuts example. It's just going to be the sum of the number of shirts and the number of pants. It's like you list out all the shirts, or you place all the shirts and pants on the bed or something, and you just need to pick one, right? So in other words, you will have 9 plus 5 to pick from. So 9 plus 5 will give us 14. 14 different options. Now, these examples are straightforward, so we don't really need set theory for these examples, but we still need to know how to do that. So let's see which one's easier here. Okay, it doesn't matter. So let's start with number 2. I need to erase this, guys. So if anyone's writing, take it down and I'll erase this. Okay, so these are the 2 examples here. These are the answers, right? The diagram doesn't matter. Okay, so let's just remember the answers. Number 1 was 45. So let's see if we can work toward that using set theory. So if we're using set theory, then we need to represent the shirts and the pants somehow as sets. So can we do that? Let's just say the shirts, for example, will be a set called S for shirts. And in that set, we will say S1 represents shirt 1, S2, S3. This goes all the way up until S9. Okay. And a set for the pants, we'll just call it P. A set called P, which goes from P1 all the way up until P5. So question 1 was, how many outputs can you make? I think this one is a bit of a longer one, but that's okay. How many outputs can we make? Now this answer, which we will see just now, the principle to tell us this is that, okay, guys, whoever's doing that, please stop. Okay, so as I was saying, guys, please. Okay, as I was saying, the answer to this question is just the cardinality of the Cartesian product. So stuff we have to recap here. The cardinality of the Cartesian product will give us the same answer that we got without using set theory. Now let's check that. So the Cartesian product, if you guys remember, if you don't remember, it's okay. We'll recap it here. I'm going to keep this line outside for cardinality. It's going to be a set which represents every coordinates that we can make using the sets S and P. So the first coordinate we can make takes S1 and matches it with the first element from the next set. And we just do this for we first do S1 for every element from the second set. So S1 with P1, S1 with P2, and so on. S1 with P3. And this goes all the way up until P goes to 5. So all the way up until P5. Right, that's the first line of our cardinality. The second line involves the second element from set 1, which is S2. And then the same thing. We'll just take every element from this set and combine it with S2. Right, so that will be S2 with P1, S2 with P2, S2 with P3, and so on up until S2 with P5. Okay. And now if we keep on doing this, we will eventually end up with a lot of these, eventually with S goes up to 9. So S9 with P1, S9 with P2, S9 with P3. That goes up until S9 with P5. and the line outside for cardinality. So we've done this for simpler sets before, but it's the same idea. And the cardinality tells us basically we just need to count all the elements in the set. That's what cardinality is. It's just the size of a set. So the size of the set is given by just counting these. That's going to be 1, 2, 3. Now we didn't list all of them, so we can't count them physically. But if we did that, we would end up getting 45. So this is a bit of a long way to do it. Maybe as a proof, but not for a specific question. So I'll show you the shortcut way now. Yeah, unlikely you'll get this proof, but I can never say never with these things. Yeah. Okay, so the shorter way to do this, which we will learn in a moment, is that the cardinality of a Cartesian product can be shortened to, what was it? It was the cardinality of the first set times the cardinality of the second set. Right, and this, okay, let me just check the condition. I'm sure that was it. Where is it? It's down here. Yes, this is the one. Right, so this is what we just wrote above. So that's the thing. So this is right here. Right, and can we see that this is essentially, we're multiplying two dimensions together. It's kind of like working out an area. It's like working out the area of this list here. Okay. Yes. Yeah, so essentially just having these two numbers, which you can easily work on because cardinality of S is just the size of S, right? The size of S is just, it's 9 elements long. The size of P, it's just 5 elements long, 1, 2, 3, 4, 5. Plug those in and you get the same answer. We can write properly, that would be nice. 9 times. It's 45. Yeah. 5, thank you. 45. Yeah. So first one, second one, yeah. Yeah, that's it.
Oh, we have to prove it. We have to do the wrong step.
No, you just use this formula unless they ask you. I wish I set the test that I can tell you exactly. Okay, so that was number 1. I think number 2 is much quicker. I'll do that here. So number 2 was a question, if we pick only a shirt or a pants, how many options do we have? And that's the same as taking the union of both the sets, S union P. I think cardinality, yeah, because we want a number. So cardinality of that. Yeah, so this is one way to do it. And we can see the union of these sets. Firstly, if we just take the union, it will be one big set with all of these in it as elements, right? If we forgot that, it's okay. Just a quick recap, the union of these two sets will look like one big set with S1, S2, and so on, P1, P2, and so on. Just one big set, right? That's the union. So the cardinality of the union is just the size of that set, and it's clearly just going to be the size of this plus the size of this, right? That's what you will get. So that is the same as just the size of S plus the size of P, which we know to be 9 plus 5. I know my 5s look a bit like S's, but anyway, so that's 14. But just one thing I should mention, that this condition that we're using here, number 2, oh, that's very bad. Try and do that better. This condition here, that I just put a box over, it only works under a certain condition. And that condition is that there's no overlap between S and P. They don't have any elements in common. Right here, that's no problem because they shirts and pants. They're clearly different things. But another way to state that condition is that S intersect P must be equal to the empty set. That's another way of saying there's no overlap between S and P. Okay, and I think that's written here in the condition, right? It's given here. There's no overlap between here, they call it A and B. But in our example, S and P. If there's no overlap between the two sets, then you can use this rule that we just derived at the bottom. Oh, yeah, we will do that. Okay, and we have an optional example here. Let's see if we need to do it. A recap of what the Cartesian product looks like for two sets. Do you guys want me to do this example? Cartesian product recap. Okay, you guys are good. Yeah. All right, perfect. If you want to recap it, you can go back and check what we did before. And this is basically just the long story I did earlier using set A and B. Okay. Now what do we do? Okay, so here exactly now we're in a place where we ask what happens to the rule we just learned, which was, I think, the multiplicative principle for sets. No, sorry. Let's just check which one was which. The one with the union is the multiplicative principle. Yeah, this one is the additive principle. So what happens to these rules when we have overlap between the sets? So let's check. Okay, so let me read the story and see if we can make sense of it. Okay, so while we're thinking about sets, consider what happens to the additive principle where the sets are not disjoint. In other words, there's some overlap. Suppose we want to find A union B, and we know that the cardinality of A is 10 and the cardinality of B is 8. That's all we would have needed earlier, right? Earlier, we would just add these two together to get the union. That's what we would have done. But if there's some overlap, then we need more information. And the information we need is how many elements are in common between the two. In other words, what's the cardinality of the intersection? And we just take that number and subtract it from what we would have done before. So we would have just taken the cardinality of A plus the cardinality of B before. But if there's some overlap, we must then subtract that number of overlaps. So if there's 6 elements that are common or 6 elements that are overlapping, we just subtract 6 from what we did before. Right? So we'll see a more concrete example. I hope so. We have, yeah, we do. Okay. But that's not so, okay. Let's make an example. Let's make one example here. I'll use the same numbers so we can incorporate things with this example. Let me just think of something. Let's suppose we have a set of people who own, I don't know, cars. I'm always using cars. You guys got another example, a better example? Cars is fine. Okay. All right. So let's say set A is the garage of person A, what he owns. And so let's say he owns cars is going to be a long thing to write. Okay, it's fine though. I'm just you can draw them. Oh, okay, we shorten them. So I'm going to try to make them distinct. Cars all start with similar letters though. So this guy owns a Lamborghini, a McLaren, Toyota, S can be so many things. Subaru, I don't know. Ford, BMW, Porsche. We should put 10 here. 1, 2, 3, 4, 5, 6. Someone give me 4 more. Bosch. Range Rover. Range Rover. Thank you. Kia. So I put C here. Honda. Thank you. How many more do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that it? We got 10 here. So we're fine. Okay. So we forget what these stand for. It's okay. They're all different letters. That's the important thing. Set A. Now we need to think of more now. That's why cars stick out. Okay. Set B. Audi. Yeah, okay, let's see. We got a good start. Audi. But now let's see. We need to think of how many to the second set have here? 8. But from this 8, we only need 2. Just give me 2. So I need 1 more. Listen, thank you. And then the rest I'm going to make them overlap. 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so we clearly have some overlaps here. Only two things don't overlap. So if I were to ask the question, maybe let's formalize this and write it down as a question. Can I maybe type instead of writing words here? Make life a bit easier. Okay, so let's type here question. Make that a bit bigger. From I'll say garage A and B, how many cars do I have to choose from? Okay, is the question clear to you guys? We have two garages here with all different cars. I just need to pick one. One car. It's a nice garage too, so good options. Okay, so the way we would do this is we would say A union B. Let me just make sure it was A union B, right? A union B was the thing. Yeah, A union B. Sorry, I'm just checking. A union B. And before, what we would have done is just said it's equal to the cardinality of A plus the cardinality of B. If we do that, though, we're counting overlaps. Right? Because from both garages, we can get Lamborghini, McLaren, Toyota, and Subaru. Right? So we don't count the overlaps. So we subtract the elements that are in common. So the cardinality of the intersection gives us the common elements. Right? Maybe we should work this out explicitly so we can see it in case we forgot how to do these things. So let's work out A intersect B in this case. So can you guys tell me what that set will look like? The common elements between both. LMTS, right? That's it. Perfect. LMTS. So how many is that? What's the cardinality of that? It's just 4 elements. So the answer to this, we can work it out now. The cardinality of A is, what did we put? 10 here. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10. Cardinality of B is just 6. So add those together and then subtract the common elements. Subtract 4. That will give you the number of options that we have. Right? So it's going to be 16 minus 4, which is 12. You have 12 cars to pick from. Okay. I needs attention, but it's recording. That's weird. Please tell me we started the recording. Yeah, we did. It's still recording. Okay. Okay. Perfect. All right. So now I'll give you guys just one more example and then we'll stop. Or you guys want to try this example at home? No. For me to do it here. So do you guys want me to do it instead of you trying it? Yeah. Okay. All right. Fair enough. I asked. You gave me an answer. That's fine. Okay. All right. Okay, so let's see this one. I think it gets a bit complicated. Hopefully not. So the example, let me just read it. It says, an examination in 3 subjects, algebra, biology, and chemistry, was taken by 41 students. The following table shows how many students failed in each single subject and in their various combinations. Okay, so first let's understand the table. It's a very depressing table. It's a table of people that failed. Okay. So subject, they just labeled A for algebra, B for biology, C for chemistry. So this tells us 12 people failed algebra, 15 failed biology, and 5, sorry, 5. I get a bit dyslexic sometimes. 8 failed chemistry, 2 failed algebra and biology. So that's what that means. 6 failed algebra and chemistry, and so on. 1 failed everything. All right. It's 1 guy. It's okay, he can come back. Maybe he'll make it for the sub, who knows. Okay, so now the question is, how many students failed at least one subject? And if you look at this table, it's actually difficult to tell from this table if they failed at least one. So what we would do here, I'm just going to skip ahead since you guys want me to do it instead of you, is we draw a Venn diagram. A Venn diagram would tell us everything we need to know. So do I have space for that? We'll make space here. And the Venn diagram must first contain, let's put A for algebra here. We'll make another circle to represent chemistry. Okay, that's very badly done. Do that again. Chemistry, let's make it like this. And this one here for biology or whatever. Oh, that's terrible. Let's get the proportions right at least. Okay, good enough. So I'll label this one A, B, and C. Right, and in this, we're putting the information of how many people failed each subject. Actually, we should have a universe here as well, right? So let's make a square. Thank you. A square outside for the universe, and that universe contains all the students, those who passed and those who failed. Yes, correct. Okay, so in circle A, we must have 12 students in total. Let's think for a second. Circle A will contain 12 students. So there's a way to do this. Okay, so I'm going to do it like this first, just to overly simplify the thing. I'm going to just draw 12 lines here. Okay, but we have to be careful. Maybe we should start from here. It's easier to start from here, the intersections. So the intersection where someone failed everything will be right in the middle. And that's one student failed everything. Right, and the other intersections, which are given here, so biology and chemistry, that intersection is this one here for the BC. So there needs to be 2 students here, right? No, sorry, 3. 3 students here. We already have 1 in this intersection, right? There's already 1 here, so we need another 2 there. So I'm going to write 2 here. So in total, in that intersection, we now have 3 students. Am I going too fast, anybody? So far, so good. Now the other intersection, which is the AC intersection, we need 6 there. So that's this intersection here, the AC. We have 1 already. So 5, right? So we just need 5 here. So we put 5 there. And similar now for the AB intersection. AB intersection needs 2. Where's that intersection here? The AB intersection needs 2. So we already have 1 there. So we just put another 1. Okay. Now we can do the individual things. We can go to the A, B, and C and just pull in what we need to. I'll leave you guys to do that. I'll do it here as well. You can check what I'm doing if you need to. For A, we need 12. We already have 5, 6, 7. So we need to just fill in the leftover. Right? Is that 5, 10, 11, 12. So I'll put 5 in A. And you can just check your work as you go, right? You can check how many are in the circle here. 5, 6, 7, 10, sorry. 10, 11, 12. 12 in the A. Does it coincide with what's up here? Yes, it does. So we know we're not going wrong. You can check as you go. Okay, so in B, I need to have 5. So I need to have 5. We have 2, 3, 4 already. So we need 1 more. We need 1 more here in B. And in C, we need to have 8 in total. So we have 5, 6, we have 8 already. Right? So here you can just put a 0 or you can just leave it blank. Either way. Go past. But we only worried about how many failed. So you can include that if you want to. So how many failed? It's a very bleak question. I'm not worried about the passing students, unfortunately. So how many failed will be you just add up all these numbers in here and you'll get how many failed at least one subject. So just add all these up. So let's start doing that. We'll say 5 plus 1 plus 1 plus 5 plus 1 plus 2. What's that? 10, 11, 12, 13, 14. I'm getting 15. So 15 failed at least one subject. So we see here that a Venn diagram is a very useful thing because to work it out without that is, well, I wouldn't know how to do it. It's a bit confusing. Okay. Yeah, so guys, maybe here is a good place to stop. If you have questions, you can ask me before we call it off. Okay, you guys are ready to go. All right, then I'll see you guys next time.